three classic theorems in mathematics: Green's theorem, the divergence theorem, and then Stokes' theorem. All three can be shown to be equivalent in some form, particularly in the plane. Here, Green's theorem seeks to evaluate the line integral by using a double integral, and it uses to its advantage the partial derivatives. The theorem here, Green's theorem, uses a condition for the region. It seeks to have the region to be what's called simply connected. We say that a simple region or a curve is said to be a curve that does not cross itself. A simply connected region is said to be here, or the region is said to be connected if every simple closed curve in R encloses only points that are in R. And I think the graphical illustration down here is apropos. So you see here an example of a simply connected region, and then versus the example of a region that is not simply connected. Now, if the region is simply connected, then we can examine the energy flow along the so-called path of this line integral. And by examining that, we can get it by looking at the so-called relationship between the partial derivatives. And so that's what we'll do. So the theorem says that let R be simply connected region with a piecewise smooth boundary, C, oriented counterclockwise. That is, that C says is traversed once so that the region R always lies to the left. So in other words, if you're moving along the path, you're moving counterclockwise, so the region is always to the left of the path of which the particle is moving. That's for containment. So if M and N have continuous first partial derivatives in the open region containing R, then the line integral can be computed by using this double integral associated the way it is. Let's see. Here we use Green's theorem to evaluate the line integral. Notice that M is equal to y minus x, and N is equal to 2x minus y. So then the partial of N with respect to x is equal to 2, and the partial of M with respect to y is equal to 1. Now, we need to determine the region. This is the region R. Here, to do that, we need to graph. By graphing y equal to x and y equal to x squared minus 2x. So if you look at the graph, so the line y equal to x does that. And then this curve, y equal to x squared minus 2x, is a parabola. It's a parabola that has x-intercepts at 0 and 2. So it does that. So you see the function that's above and the function that's below. And so the function that's below is x squared minus 2x, and the function above is y equal to x. Now we need the points of intersection to determine the bounds for x. So to do that, we just set both of these equations equal. So here we get x squared minus 3x equal to 0. So x times x minus 3 equal to 0. Do you see that x equal to 0 and also x is equal to 3? So the region here, x is bounded from 0 to 3, and then y is bounded below by the curve x squared minus 2x, and is bounded above by the line y equal to x. So that's what we need, and so the line integral here is computed by the double integral over the region of the partial of n with respect to x minus the partial of m with respect to y dA. We have the information that we need. Here x will go from 0 to 3, and then y goes from x squared minus 2x to x. And the partial of n with respect to x is 2, and the partial of m with respect to y is 1. So this is 2 minus 1. This is dy dx. Thereafter, just integrating a double integral, so that's not bad. So we integrate with respect to y. Space is running out, so I'm just going to put it in here. So this becomes y evaluated from x squared minus 2x to x. So that gives us the evaluation of y at x minus the evaluation of y at x squared minus 2x. This is dx. So this is the integral from 0 to 3. This is x minus x squared plus 2x. So this becomes 3x minus x squared. This is dx. We integrate, we get 3x squared over 2 minus x to the third divided by 3. That's evaluated from 0 to 3. So this gives us 27 over 2 minus 9. And so this gives us 9/2. Okay. Now you understand that the line integral is being computed basically by the area that's contained within the curve. So instead of the line integral will calculate the energy along the path of the curve. But Green's theorem says you can find the energy by investigating basically the area that the region of the curve has contained. I think that's better illustrated here. C is the boundary of the region lying inside a rectangle bounded by x equal to -5, x equal to 5, y equal to -3, and y equal to 3, and outside the square bounded by x equal to -1, x equal to 1, y equal to -1, and y equal to 11. So we're going to do some straight line drawing, so I need some help. We're going to have the xy plane. You got a rectangle. Make it bigger. Stop there. You get the idea. Then the square. Is that a square? Looks like a rectangle. A little bit better. Takes like forever and a day for me to do it. So x-axis, the y-axis. X goes over to -5. To 5, and then y goes up to 1, and then down to negative. Oh, this is wrong. This is 3, -3. So if that be the case, you see that the length here is 10, and the length here for the top was actually is 6, and this is 10. Blind, I can't see. I need to wear those glasses like DMC, or sunglasses like DMC, whatever. Anyway, this is 6, and then this side right here is 1 plus 1 is 2, and the same thing for the top. It's a square. So we have the outer area, I'll call it a sub 2, and then we have the inner area, a sub 1. So a sub 2 is 6 times 10. That's 60. A sub 1 is 2 times 2. That's 4. Right? And so here, this is use this same line integral to calculate the line integral here based on different path that they give in number 7 all the way to number 10. Right? So all this right here is still usable for numbers 7 through 10. So for this problem, this line integral is written in differential form. M dx plus n dy is this double integral, right, over the region. Remember, this came out to be 2 minus 1 with respect to dA. So here, this is 2 minus 1. The change in the area, there it is, 60 minus 4. That's it. In exercise 11:20, use Green's theorem to evaluate the line integral here. So this is m and this is n. So the partial of m with respect to y is 2x, and the partial of n with respect to x is 1. We need that for Green's theorem. Look at this graph. We have y equal to 1 minus x squared, and then y equal to 0. That's this line here, right? So we have containment. So this becomes the boundary. So you see that x goes from -1 to 1. If you look at here, what you're calculating, this is the double integral. X goes from -1 to 1, and then here for the curve, the bottom function is y equal to 0. The top one is 1 minus x squared. And this is the partial of n with respect to x, which is 1, minus the partial of n with respect to y. That's 2x. This is dy dx. So this is the interval from -1 to 1. We integrate with respect to y. So this is y times, just write this is 1 minus 2x times y. Y is evaluated from 0 to 1 minus x squared dx. This is the integral from -1 to 1 of 1 minus 2x times 1 minus x squared, right? Dx. We'll simplify that, and then we integrate. So this is 1 minus x squared minus 2x plus 2x cubed dx. So let's integrate now. So we get x minus x cubed over 3 minus x squared plus 2x to the 4th divided by 4 is x to the 4th all over 2. It's evaluated from -1 to 1. We plug in x equal to 1, we get 1 minus a third minus 1 plus a half. Now it's minus a -1, which is plus 1. It's minus this minus, which is positive. This is -1 to the third. So this is minus a third. Minus this minus is plus. -1 to be squared is positive. So then it's minus a half. So the halves cancel out. And let's see here, 1 minus 1 will cancel out. So we have left 2 minus 2/3. 2 minus 2/3, that's 4/3. All right, what about this one? Here the region is based on the circle. So the region R goes from 0 to 4, and theta goes from 0 to 2 pi. Now if this is m and this is n, so the partial of n with respect to x is equal to 2y, and the partial of m with respect to y is negative 2y. Right? So the line integral that you're wanting to compute is the double integral. Here this is the partial of n with respect to x, that's 2y, minus the partial of m with respect to y is minus a minus 2y, so that's 2y plus 2y. And we'll say this is dA over the region. Now let's put in what the region is. I'm going to calculate this from 0 to 2 pi. This is from 0 to 4. Because this is 4y, right? But 4y, y is r sine theta. And for the polar coordinates conversion, you got to have r dr d theta. So this is r squared. No, what is that? R squared sine theta d theta dr. Integrate with respect to theta. So I get -4 times the integral from 0 to 4 of r squared cosine theta evaluated from 0 to 2 pi. So it's dr. I'm calculating the d theta here. Cosine of 2 pi is 0, or is 1, excuse me, then minus cosine of 0 is 1, so you get 1 minus 1, we get 0. All right. So the region is, the radius goes from 0 to a, and then theta goes from 0 to 2 pi. They put no other restriction on the angle, so here it's given to theta goes from 0 to 2 pi. So this is m, right, and this is n. So the partial of m with respect to y is -2 e to the x sine 2y. And the partial of n with respect to x is -2 e to the x sine 2y. It's conservative. It's a closed path, so the result is 0. Now this m dx plus n dy is this statement here, of which I don't want to have to write that, so I just write the generic. This is equal to the double integral over the region, right? And then these partials here. Partial of n with respect to x is -2 e to the x sine 2y minus this guy. That's plus, minus that minus is plus. dA. Well, they're opposite, so we get 0. Two more and we're done. What about this region here? The graph. This is y equal to x, and then the square root of x. So we get that moon. We get the moon. What's up in the moon? We get the moon pie, of which I hated when I was a kid. But anyway, let's set these two functions equal to determine the values for x. So here x is equal to the square root of x. This gives us x squared is equal to x. So we get x squared minus x is equal to 0. X times x minus 1 equal to 0. So we get x equal to 0 and x equal to 1. So the region, the function that's above is the square root. The function that's below is the line y equal to x, right? So we got that. This is m. This is n. The partial of m with respect to y is negative sine y, and the partial of n with respect to x is y minus sine y. That's a y, not that guy that's on Star Trek when they get to the bar and that funny looking dude that looks like a lowercase g. Yeah, that's not what that is. Well, almost reminds me of it. Oh, okay. So here, the line integral is equal to this double integral, and we have the information here. X goes from 0 to 1. Y goes from the lower function x to the upper function, which is that curve, the square root of x. So this is the partial of n with respect to x, which is y minus sine y, then minus the partial of m with respect to y, which is minus this minus, that becomes plus sine of y. And this is dy dx. Dx. Well, that's good. Those sine y's cancel out for us. So this is the integral from 0 to 1, the integral from x to the square root of x of just y dy dx. You can't convert to polar coordinates because the region is not given by a circle or a sector of a circle, right? So 0 to 1, integrate with respect to y, gives us 1/2 y squared, which is evaluated from x to the square root of x. And then dx, we get 1/2 times the integral from 0 to 1. Evaluate the y squared at the square root of x to be squared minus here x squared dx. So this is 1/2 the integral from 0 to 1 of x minus x squared dx. So this gives us 1/2 sitting there, and this is x squared over 2 minus x cubed over 3, evaluated from 0 to 1. So we get 1/2 times brackets 1/2 minus 1/3. So we get 1/2 times here 6. This is 3 minus 2. So we get 1 over 2 times 6 is 12. The last one. So this is m, this is n. So the partial of m with respect to y is -3, and the partial of n with respect to x is 1. Here, we have two circles, right? Circle within a circle with a radius 1, and a circle with radius 3. And you're looking for the boundary of the region lying between these graphs. So as Deacon Arrington would say, oh boy. I think you get it. Better stop. So the region, the radius goes from 1 to 3. And then theta goes from 0 to 2 pi. So this line integral of m dx plus n dy is equal to this double integral here. R goes from 1 to 3. Theta goes from 0 to 2 pi. This is the partial of n with respect to x. That's 1. Minus the partial of m with respect to y. That's a -3. So it's 1 minus a -3. I do not like parentheses on top of parentheses. Let's use brackets. This is r dr d theta. So this is 4 on the outside times the integral from 0 to 2 pi, the integral from 1 to 3 of r dr d theta. Integrate with respect to r, so that becomes r squared over 2. So 4 divided by 2 is a 2 times the integral from 0 to 2 pi. And this is r squared, evaluated from, just used to saying from 1 to something, right? So from 1, well, from 0 to something. So this is from 1 to 3, and then out here we have d theta. So here we have 2 times 3 squared minus 1 squared times the integral from 0 to 2 pi of d theta. That gives us 9 minus 1 is 8 times 2 is a 16. Integrate with respect to d theta. 1 times d theta, that's just theta, evaluated from 0 to 2 pi. And so what you end up with is 16 times 2 pi. So that gives you 32 pi. Now I'm done, and what I've done was a day or so ago I recorded the lecture for the last section in this class, so kind of went in the reverse order. So I've already recorded the lecture for 15.8. I think 15.8 is the last section, and I do plan hopefully to come back and do something extra just on the side, something that you may need for vector analysis if you take that course. Yeah, 15.8 was the last section, but this is the last section that I'm recording, and this whole summer I've been in the process of recording all of the videos, lectures for Calculus 1, 2, and 3. So it's been a very tedious task. Thank you for your patience. And so I've been here at my desk doing this, and just looking at this screen, writing on the screen just hurts my neck. And all of that, and then I get hungry because I don't eat much, but I eat often. And so but here's where I've been working, and so this is just an image of my desk with the notes and everything just worked out before I come to the video to record, and just the image of where I am here at the college in this space, and it is just an image of the screen and everything that I see that you probably can't see, and just junky office, as you know, that's just how it is, and that's what we do. So I hope all is well with you. You go well and stay well. God bless you. Thank you.